Right. So, welcome. And in this, I'm going to discuss the attitude determination and control unit of the CubeSat. I've come up with a schematic that will help constitute that board. So, I'm just going to discuss how it all fits together, how everything fits together, and the functions of each of these modules. And then, we'll see how it goes. Now, the attitude determination and control unit, right? So there are three things there. So attitude is the location of an object in space, right? Whatever space, physical space or space literally outside there, doesn't really matter. But attitude determination, so you have to determine your attitude, which includes things to do with physical motion, right? Things to do with your speed, acceleration, vector velocity, angular velocities, vector velocities, displacements, location, physical location. And then you have to control that. So determination and control, you have to control that depending on how you want it, if at all it needs to be controlled. So for a CubeSat, you need to determine all of that and then place your system or device in the right orbit, in the right direction, so that it can achieve the mission that it was meant to achieve. Right. So I'll discuss the units that I've designed in this board that constitute that. And I'll kick off with the voltage regulation part. Again, as I've mentioned in the other videos, is that I'm using a dedicated approach to designing this power supply. So it means that I am doing point of load regulation. So regulation is done where it's being used, which means that I'm getting raw voltage 5 volts right here from the EPS, the electrical power supply. And then I have a header switch or header pin here that can turn on and off the board manually. And therefore that voltage is passed on to the 3.3 volts regulator. So 5 volts, 3.3, and then 3.3 is used to supply my systems with voltage, right? Now there are a couple of things that needs to be addressed at the power supply so that we meet the CubeSat designs, the specification standards. The first thing is they recommend to have at least 2 inhibit switches. Right now I have placed only one in this schematic. I will place another one maybe when I'm done with the other parts of the schematic, as I will explain later. But basically inhibit switch is nothing fancy. It's just a switch that is used to prevent some parts of the system from turning on while being launched or during launch, or rather it turns off the systems until your device is in orbit, right? So it's called an inhibit switch. So to do that, I used a regulator that has an enable pin right here. So this enable pin from the datasheet of the regulator means they say that if you write it high or if you connect it to the V in, they'll be turned on by default. And if you connect it low, you will turn off the regulator and there'll be no output voltage, right? So it means if I am able to control this, I can be able to control the on and off times or switching of this TDC board. Therefore, I've connected this EN pin to a micro switch, right? A switch like this one. This is a micro switch. It's just a spring-loaded switch that can be used to turn on and off the system depending on the state. So you can see it has 3 pins. A common pin normally open and normally closed, right? It's actually labeled right here. Now, to do that, assume these 2 components. The 5 volts come from the EPS, right? Part of it branches into this switch, into the normally closed, and goes to the enable pin. So by default, this board is powered on ground. Okay. Now when you insert this CubeSat into the deployer pod, this switch will be on the face or on the edge of the CubeSat, so it will be pressed against the deployer pod. When you press this switch, it will turn to the normally open, right? So it will turn off this enable pin. The enable pin will be disconnected, and consequently the regulator will be off, and no power voltage will be supplied to your downstream systems or components. Okay, so how do we simulate that? One part of designing such a system is to make sure that you can be able to test your mechanisms on ground. So I have put two header pins here that enable us to turn on and off, or to play around with the normally closed and normally open parts to see how it behaves during launch and after launch. Right, so I can activate this normally closed switch by just closing this header pin, or deactivate it by removing it, and likewise consequently deactivate it by turning on and or off normally open switch. And I've come up with a truth table for that, but I won't go into the details for that so much anyway. It's a simple testing procedure, right? So there are some don't care states and invalid states. For example, these two should never be on because they'll short the pin. And next is just an LED to indicate when this when this inhibit switch is turned on or off. And yeah, I think that's all with the power supply and the inhibit control switches, right? So these are POD testing headers, other the pod, the deployer testing switches. Right, so the other thing for determining attitude is now how do we get the accelerations? So the best calculate to use for that is the 6050 NPU, a very simple basic chip, and it gives us all the data that we need. So the NPU 6050 will give us the XYZ accelerations plus the gyroscope values, which means the angular velocity of the CubeSat in space. Okay. And the data rate is pretty high, which is cool. Most people, based on my research, have used this, which is pretty common, right? Next thing is I have put another accelerometer just for redundancy and to try out to see how those sensor data will combine with each other. So I've put an ADXN 345 accelerometer at this point. Also will give me acceleration in 3 axes, purely acceleration through I2C, right, at this point. And I can do sensor fusion between this and that, those two accelerometers. So the vector velocity is fixed at that point. And now the good thing is that once you have acceleration and angular velocities, you can easily derive a lot of other data points, things to do with displacement, velocities. You can derive a lot of roll, pitch, yaw angles, everything to do with that. And yeah, that's that about the accelerations. Next thing is let me go with the attitude determination first. So we need to determine the location of the satellite. So I've put a GPS module for that. So I've used the ATGM 336H module. It's a pretty strong and robust module that has access to GPS, GLONASS, Beidou, Galileo, all of that access to GPS signals. Okay, so this is a pretty basic schematic for GPSs. This GPS has a reset pin, so we can easily reset the GPS from the MCU through a transistor. So you can see that this and reset is active low, so you need to pull it to ground to activate it, and that transistor driver does that. Next thing is the VBAC requires 3 volts, so you have to have a regulator to drop 5 volts from, to drop from 5 volts to 3 volts, which is okay. I have put an interface for UART, and an activate pin. Interface. This GPS uses both I2C and UART. So why don't we have both and experiment with whatever data we get through either of the two interfaces? The other thing is, of course, an LNA for the antenna. This is a low noise amplifier connector for the antenna, and a UFL SMT connector here. Basic standard for, for the antenna, right? Yeah, so this should not be placed. Let me just disable this. What? No. Okay. Now we have the other thing we need to connect is the orientation of the CubeSat with respect to the sun. Right? So now remember that this CubeSat has 6 faces. It's a cube. So you need to know at which face is pointed towards the sun. The only way to know that is to measure the ambient light, right? So we measure ambient light using the photo transistors. And the best photo transistors I've seen, cheapest for my use case, is this EMT 6000 X01 sun sensors. But it's just a photo transistor with an open, with a collector here. And you can connect those points to the MCU. So it has a VCC supply, ground, and the signal, right? And the signal. So depending on which phase is pointed towards the sun, you can actually literally actuate your detumbling mechanism to know whether to orient your CubeSat. Maybe now here I'm discussing like the logic of the firmware, but basically you want your CubeSat, for example, to collect the maximum amount of light based on if it's not on the eclipse side, if it's not in darkness. So these antennas are used for just that, to know which side is pointing to the sun, right? Okay, so you can see these are 6, 1, 2, 3, 4, 5, 6 sensors, right? 6 sun sensors. You can connect directly to the MCU. So from this point to the OBC MCU, which is this one, and because they're giving you analog voltages, you need to use the ADC converters, right? But if I use that, I'll have 1, 2, 3, 4, 5, 6 pins will be gone that easily. And since I'm not done with some of the systems, I don't want to risk, giving off all those pins to a single point. So what I did, I connected these sun sensors through an analog to digital converter chips, external converters that communicate through I2C, right? So by doing this, you have just used 2 lines to connect 6 sensors. You see, someone else would have used maybe a port or IO expanders. But since this is purely an analog to digital conversion problem, why don't we use an analog to digital converter chip for that purpose? So these are ADS 1015 12-bit ADCs. 12-bit will give me very high resolution. It's because the sun can be in space. The sun can be like literally, if you are close to the eclipse, can be very low values. So you need to get the least resolution. I mean, the maximum resolution that you can get. So 12-bit is best. So you have options between 8-bit, 10-bit, and 12-bit. And that data will be sent to the MCU. Now, the problem with the ADS 1015 is that it only has 4 channels, and I have 6 sensors, which means I need to use 2 of them. So the first 4 are connected to the first ADC, and then the last 2 are connected, and then these 2 pins are not used, which is no problem. That will be super good. So by I2C again, and you're good to go. So we have determined the data for that, and then maybe an extra temperature sensor. It's not really very necessary for this board, but it doesn't hurt to have it. Right now, The other question is, how do we now control this attitude? So assume we have found out that our satellite or CubeSat is tumbling, right? It has got into an uncontrolled roll. How do you control that? Normally in big space vehicles, they use thrusters, right? So you can burn thrusters to control your vectors. But for a CubeSat, which is small, it's not viable technically and economically to put fuel in such a small space, right? There's not actually even enough space to do that. So we use what are called magnetokers, right? Magnetokers are just components that react to the Earth's magnetic field. Magnetokers, right? They are components that react to Earth's magnetic field, and they are nothing but solenoids or coils of magnetic ferrite wires that can be activated to just react or push against the Earth's magnetic field. So at this point, we are leveraging on the Earth's magnetic field to help us determine or control our CubeSat. So you see, this is just nothing but coils of wire wrapped around. I've not gone deep into them, but I think they are wrapped around maybe a ferrite core or something like that, right? That you can push against the magnetic field of the Earth. So we will design this also for our CubeSat and integrate it and see how it functions. Now, how do we measure the magnetic field of the Earth? We use a magnetometer. This is also a basic compass-ish, right? So there's a sensor that can give you the values of the north-south magnetic field strength of the Earth. Based on whatever data you get here, you can easily control magnetoker, right? So you can see here I have put like a to-do list basically for designing the magnetokers themselves. Okay, so this magnetometer MLX 9393 will give me the strength of the north-south fields of the CubeSat, and I can actuate the magnetokers based on the data from these points. Right. The other small element is the board insert detect. I discussed in the comms board. Basically, is a way of knowing now I've already inserted this board into the stack of the CubeSat, and there's nothing but a pin pulled low, so we can sample that pin on the onboard computer and see whether this board is inserted or not. Right, and then we have a couple of screw holes on each corner to help with the mounting, draw standoffs, and the other bigger fish is the intersatellite architecture connector, ASA connector. Right, let me remind myself that's abbreviation. Connector is what? Okay. Right, ISA connector. So basically it will be used to couple the different boards together, and this ISA connector is common, or rather is standard across all the four boards that we are designing for the CubeSat. And in case we want to pass signals from one board to the other instead of using wires directly, then just use this stackable connector, and I think I've discussed this enough. So at this point, it's nothing new really, and it goes on adding new pins or new connections. Maybe now when you design the magnetoker or something, we'll add new connections at this point. Right. So I think that is the much and the little about this board. It's a very basic board, obviously, but it's very, very crucial to the operation and successful mission of the CubeSat. So again, to remind you that this CubeSat is meant for Earth observation, right? So it will pass over a given area and take monochrome pictures or VGA pictures of that specific area based on the commands or the mission commands from the ground station. So it means that if this CubeSat is not pointing the right direction during the mission time or the mission period, the mission will have failed, right? So this board is really critical to help us determine and control the position of that CubeSat. Now, maybe one thing to mention is there are two things I want to experiment with for the attitude control part. Based on the research I've done, there is a magnetometer, which I've easily discussed right now a few seconds ago, and then there's a reaction wheel, right? So reaction wheel is basically a momentum controlled wheel that acts opposite of the roll, pitch, and yaw angles to counter the rotations and the rolls of a device moving in space. But now the problem with the reaction wheel is that it's mechanical. First of all, it has moving parts. It adds moving parts to a CubeSat, which in space is like the last priority most of the time because of wear and tear, and you can't go to grease or lubricate a motor bearing in space, right? But on Earth, so I think it's interesting to just try and design a reaction wheel and see whether it will really help us in controlling this attitude of the CubeSat. Yeah, it's just gonna be interesting. I just want to do it out of interest and see if I can really build it. And I mean, I know I can build it and see whether I can really use it for this project. Maybe it can be a redundant system together with the magnetokers. Okay, so those are two most commonly used attitude control mechanisms, right? So yeah, so at this point, just to give a brief catch up on the project flow, I think we are almost done with the design, the hardware design, which is the PCBs and the schematics. Oh no, the schematics only. We have not started the PCB design. But I feel pretty confident that I am on time because the most important boards are the OBC, ADC, and the comms board. Now, the remaining board is the electronic power supply. That's the only remaining board. And maybe next week, I will be able to come up with a design for that also and review it in a video like this one. But overall, we are moving really fairly good, and I would like to extend this to take this maybe chance to extend welcomes to contribution. I released the documentation on the GitHub project repository, so it's there, web friendly and readme, so that you can check it out. So if you want to contribute, don't fail to hit me up, and I see how we can, which part you can take up. And especially that the firmware is coming up and it's gonna be extensive, so I'd rather you can lend your expertise, or if you want to learn, it doesn't have to be really expertise or anything. I'd really appreciate. It's an open source project, so looking forward to a community that can deliver, that will be able to deliver this the first DIY CubeSat from scratch. Right, so that's that, and yeah, all the best.